what we are going to do today is that we will carry on our discussions on the convergence of the solutions of a stationary convergence of solutions of nonlinear evolution equation to their stationary solutions actually. So what we did in our last class, we were discussing in particular what do you call this version of reaction diffusion equation, okay? And we were aiming to prove this result, which says that that for any initial data in this Sobolev space, okay, you can always find a smooth function that is independent of time, so it just depends on x, such that this psi is a stationary solution, okay, of the problem star, and the solution, the global solution to the reaction diffusion equation star converges to this stationary solution in long run in say H norm, okay, in H norm as t goes to infinity, where by H we mean this space actually, okay. So we had reaction diffusion equation for every initial data in this space H. We can find a stationary solution to our reaction diffusion equation such that the global solution, the time dependent solution of this equation converges in long run to the stationary solution actually of the same equation. So this is what was our aim. So what we did in our last class, we in order to study what do you call this long-term behavior for this nonlinear evolution equation, we actually developed some abstract set of results. We talked about theory of omega limit sets. We talked about its properties, some of the basic properties of the omega limit sets. We talked about the gradient systems and gradient flows actually, and then we talked about that what would be the omega limit set for the gradient flow actually. And we actually saw, if you remember, that if your gradient flow, in other words your nonlinear abstract evolution equation, okay, so this is one example of it. This theory that we did was general actually, okay. So if you have your nonlinear evolution equation, which is a gradient flow, then its omega limit set basically precisely comprises of the stationary solutions actually, okay. So the stationary solutions of the same evolution equation, okay. So that's what we did, and we also, as I mentioned, that proved that this evolution equation, this reaction diffusion equation, this nonlinear heat equation is basically a gradient flow. In other words, that this is space with the semigroup and the energy of this reaction diffusion equation, this triplet is a gradient system actually. So now since we know that the solution to the solutions to this evolution equation constitute a gradient flow, so we know that its omega limit set comprises of the stationary solutions of the same equation. In other words, such kind of what do you call smooth functions. So the only thing that we are going to prove today, and that only thing is going to take a while actually to prove, it's not going to be straightforward, is to show this actually, is to show that any solution corresponding to initial condition U0, the unique solution of this problem converges to the stationary solution of the same problem in long run as t goes to infinity. So this is what that we would like to do today actually. And then we will also study what you call the rate of convergence actually, that at what speed rate the solution U is converging to the solution psi actually, the stationary solution psi. So what is the the layout for today's discussion? Okay, so we will start with Łojasiewicz-Simon inequality. So an inequality that is crucial for studying the long-term behavior of nonlinear evolution equation, especially in particular about the gradient flows. So we will talk about this Łojasiewicz-Simon inequality. And then we will, using this Łojasiewicz, we will not prove this Łojasiewicz-Simon inequality in general, I'll just mention it, and maybe I'll just give the glimpse of a proof in one-dimensional case actually, because this inequality follows very easily from the Taylor's expansion. Now, what we do next? Next, what we are going to show, an interesting inequality, which would be a consequence of this inequality. So we will prove an inequality as a lemma, and this inequality is that if you compute the H norm of, say, this side of this evolution equation, okay, the H norm of, say, Laplace u plus u minus u cube, not H norm, sorry, L2 norm. By the way, whenever I'm gonna just write, what do you call this, I am going to mean, okay, I am going to mean the L2 norm, that this is norm in L2, okay? And if I have to say the norm in the space H, I will write it explicitly, okay? So this is the L2 norm of the right hand side of this evolution equation. What we would like to show today is that basically this quantity is bigger than or always equal to an increment of the energy of the system. In our last discussion, we also computed basically the energy of this heat equation with nonlinear heat equation, and then we also showed that this energy is basically dissipated with decreases over the time. Okay, so we're gonna show in this lemma that the L2 norm of this quantity is bigger than or equal to E of u minus E of psi, where psi is the what do you call, the psi is the stationary solution, power, I guess, theta minus 1, I think it is 1 minus theta, okay? I'll describe that later when I'll propose write the lemma more explicitly, that what is this theta and what are all the details actually. Where for now, u is the solution of, what do you call, equation star. So we like to prove this lemma, and then using this lemma, we will actually prove the theorem that I have mentioned here actually. So this convergence theorem. So I will prove the convergence theorem, and probably we will also quickly talk about the rate of the convergence as well, that okay, you know, at what rate u is converging to the stationary solution psi in H as t goes to infinity, okay, as t goes to infinity. So we will talk about a little bit about the data actually. So these two results are not going to take a big time, but these are some of the results, especially this lemma is going to take a bit actually, and then we have to be a little bit patient in order to prove this, what you call, inequality. I will try my best to go into the proof of this inequality and the convergence, proof of the convergence in detail, because what I want is to you try a similar kind of analysis for the analysis for the evolution equations that you have been assigned through study actually. Okay, so you have to bear with me and be a little bit patient actually. So let's just start. Let's just start with introducing Łojasiewicz-Simon inequality. Okay, let's introduce what do you call Łojasiewicz-Simon inequality, and then prove, or maybe just give the glimpse of a proof of it in one dimension actually. So what is Łojasiewicz-Simon inequality? It's a very important tool if you want to study the long-term behavior of the evolution equation. Now, there are several other techniques that have been developed, but this one is really the classical one actually. So let me write this Łojasiewicz for one time at least explicitly, okay? And you have to be careful that, as per our, what do you call, South Asian accent, I am saying it Łojasiewicz, but it has a bit different spelling actually, okay? Anyway, so it's a typical European name. So, A-S-I-E, Łojasiewicz, Simon, inequality. Okay, so in short, I'm going to call it LS inequality. So what is Łojasiewicz inequality? So the inequality says that suppose you have a function, okay, you have maybe a scalar field, okay, that is a map from say Rn into what you call R, and say this function f is analytic actually. Okay, its function is analytic. I hope that you know the definition of the analytic function. So this function is analytic, and say x equal to a, or with x equal to a being its critical point, actually. Critical point. Okay, that is that if you compute the gradient of f at a, you're going to get what do you call 0. So we have an analytic function with a critical point. Then you can always find, there always exists a positive constant sigma and a number theta between 0 to 1/2, okay, such that if x is a point that is in the neighborhood of this critical point A, okay, or x is a point that is away from what do you call the point A at most by the distance sigma, then the gradient of f of a or f of x, or maybe f of x minus f of a, okay, power 1 minus theta can be estimated by some constant. In other words, there exists such constant times the gradient of f at x, okay, in obviously Rn. Okay, so this is what you call the Łojasiewicz-Simon inequality, is that you have an analytic function with a critical point, then there is always a positive constant sigma and a number theta, such that if x is an arbitrary point living in a neighborhood of A, okay, with the radius sigma, then this increment of f power raised to 1 minus theta can be estimated, or this is less than or equal to some constant times the gradient of f of x actually. Okay, the gradient of f. So this is what the Łojasiewicz-Simon inequality is, and this inequality would be a crucial inequality for proving this lemma actually. Okay, but there's a lot of preparation while proving this lemma. So this lemma has a bit longer proof. Let's see that what we're going to do now based on this Łojasiewicz-Simon inequality. We will what do you call, prove the R required lemma. So here is the lemma, the interesting lemma. So the lemma, the precise state of lemma is this. Okay, so suppose that psi is is a smooth function such that it satisfies the stationary evolution equation, okay, psi plus psi minus what do you call psi cube equal to 0, and psi onto the boundary of omega is 0. So suppose that you have such psi. Then for each such psi, we can find two positive constants. We can find a sigma and a theta in 0 to 1/2. Yeah, sigma and theta, okay, so sigma is a positive number and the theta is between 0 to 1/2. So this sigma and theta are same as what you call in the statement of the Łojasiewicz inequality. Okay, then we can find, then there exists sigma positive and theta, and depending on what do you call it, psi, okay, such that you have this inequality that Laplace u plus u minus u cube is bigger than or equal to e of u minus e of psi power 1 minus theta, okay, where E of u is the energy of the problem star. Okay, so it's the energy of the problem star. So this is what the lemma that we are interested in. So for every such a stationary solution, you can find a number sigma and a theta depending on psi such that this inequality holds. And this inequality would be the crucial inequality for proving what do you call our convergence result actually. This inequality is going to take a bit time, so you have to be a little bit patient